What if the history of everything we know from the first star to the device you're watching this on is written in an ancient and universal text, a story told not in words, but in atoms? Imagine this cosmic storybook, its opening chapter drafted in the first few minutes of time itself using an ink of pure energy. This is the story of the Big Bang, our most profound and successful explanation for the origin of the cosmos. It is a narrative of creation so powerful, so predictive, that it has become the bedrock of modern cosmology. Its mathematics foretold the faint residual glow of creation's fire, a prediction confirmed with the discovery of the cosmic microwave background radiation. It explained the grand outward rush of the galaxies, the very expansion of space-time itself, and in its most stunning triumph, it provided the recipe for the original matter of the universe. It told us with breathtaking precision how much of each light element should have been forged in the primordial furnace of the Big Bang. It is a theory that gets almost everything right. Almost. Because buried within this triumphant first chapter in the fine print of the cosmic recipe is a single glaring mistake, a number that doesn't add up, a detail that stubbornly refuses to align with our observations. It's a quiet but persistent discord in the symphony of creation, a ghost in our beautiful cosmic machine. It is the story of an element that shouldn't be so rare a cosmic fingerprint that appears to be smudged. We call it the Lithium Problem, and it represents one of the deepest and most unsettling mysteries in our quest to understand where we came from, challenging the very story of the universe we thought we knew so well. To grasp the enormity of this enigma, we must journey back. Back beyond the first galaxies, beyond the first stars, to a time when the entire observable universe was smaller than a single atom in your body. We journey to a moment of incomprehensible energy, of unimaginable density and heat. This is the dawn of time, the very beginning of the first chapter. In the initial sliver of a second, the universe was a seething, incandescent quark-gluon plasma, a state of matter so extreme that the fundamental building blocks of protons and neutrons could not yet coalesce. The four fundamental forces of nature we know today were unified, acting as one. But the universe was expanding, and as it expanded, it cooled. This cooling was not a gentle process. It was a series of violent, dramatic phase transitions moments when the very character of reality snapped into new configurations. Within the first microsecond, quarks bound together, forming a roiling sea of protons and neutrons. For a brief period, these particles, the future cause of every atom in existence, existed in a near-perfect balance, constantly colliding with a maelstrom of electrons, positrons, neutrinos, and photons, their identities shifting in a frantic high-energy dance. The universe was still too hot, too chaotic for anything more complex to survive. Any fledgling atomic nucleus that dared to form would be instantly obliterated by a high-energy photon, a gamma ray acting as a relentless celestial blowtorch. This state of chaotic equilibrium couldn't last. As the clock ticked forward, crossing the 1-second threshold, the universe continued its relentless expansion and cooling. The temperature dropped below a critical point where the weak nuclear force could no longer sustain the rapid conversion between protons and neutrons. The balance was broken. Neutrons, being slightly more massive than protons, began to decay, while the more stable protons became the dominant form of nuclear matter. The final ratio of protons to neutrons became frozen in CERN at approximately 7 protons for every 1 neutron. This precise ratio was the cosmic die being cast. It was the universe setting the initial conditions for all future chemistry, for all future stars, galaxies, and life. This single number, fixed in the first second of existence, would dictate the composition of the universe for billions of years to come. For another agonizing minute, the universe was still too hot for these particles to bind. It was a cosmic waiting game. The protons and neutrons were ready, the fundamental recipe was set, but the oven of the universe was still too fiery. Any attempt to form deuterium, the crucial first step in cosmic alchemy, a nucleus made of 1 proton and 1 neutron, was met with immediate annihilation by the dense bath of radiation. This period is known as the deuterium bottleneck, a frustrating cosmic traffic jam preventing the formation of heavier elements. Then, at around 3 minutes of age, everything changed. The universe cooled to a mere 1 billion degrees Kelvin. For us, an unimaginable temperature, but for the early cosmos, it was the moment the floodgates opened. The deuterium bottleneck was finally broken. Suddenly, deuterium nuclei could survive the photon bombardment, and once deuterium existed, a furious, breathtaking chain reaction of cosmic creation was unleashed. This was Big Bang Nucleosynthesis, or BBN, the universe's one and only chance to forge the elements from scratch on a grand scale. In a frantic burst of activity lasting only about 17 minutes, the universe became a nuclear furnace. The newly stable deuterium nuclei were the essential building blocks. They rapidly fused with protons and neutrons, or with each other in a cascade of reactions. 2 deuterium nuclei could fuse to form a helium-3 nucleus, or even a tritium nucleus. Then these new creations would themselves be swept up in the creative frenzy. A helium-3 nucleus could fuse with another to form the incredibly stable configuration of helium-4, 2 protons and 2 neutrons, bound together by the strongest force in nature. This pathway was so efficient, so overwhelmingly favoured by the laws of physics, that nearly all of the available neutrons were consumed, locked away forever inside helium-4 nuclei. The process was a sprint, not a marathon. The universe was still expanding and cooling at a ferocious rate. With each passing moment, the density and temperature dropped, making further nuclear reactions less and less likely. By the time the universe was 20 minutes old, the party was over. The cosmic furnace had shut down. The elemental composition of the universe was set in stone, a primordial mixture that would remain virtually unchanged until the first stars ignited hundreds of millions of years later. This is the story our cosmological model tells us. A dramatic, precise and testable story. And here lies the triumph. The theory of Big Bang nucleosynthesis doesn't just give us a vague narrative, it makes stunningly specific quantitative predictions. It acts as a cosmic accountant telling us exactly how much of each element should have been in the universe's starting inventory. The theory is governed by a single crucial parameter, the baryon to photon ratio. This is simply a measure of the density of ordinary matter, protons and neutrons compared to the density of light photons. We have an incredibly precise measurement of this number from the cosmic microwave background, the afterglow of the Big Bang. By plugging this single known value into the equations of nuclear physics, BBN theory can calculate the expected primordial abundances of the light elements. It is a moment of truth for our entire cosmological framework. Does the prediction match what we actually see in the universe? For hydrogen and helium, the answer is a resounding, spectacular yes. The theory predicts that the primordial gas should be about 75% hydrogen and 25% helium-4 by mass. This is exactly what we observe when we look at the most ancient pristine gas clouds in the distant universe, places untouched by the polluting influence of stellar fusion. The agreement is breathtaking, a monumental victory for theoretical physics. It's like writing down a complex recipe for a cake based on the temperature of the oven and then tasting that cake billions of years later to find it matches the recipe perfectly. The theory's success continues with the trace elements. It predicts a very specific amount of deuterium or heavy hydrogen. Because deuterium is so fragile, it is easily destroyed inside stars, meaning that any measurement we make today represents a lower limit on its primordial abundance. When astronomers measure deuterium in ancient quasar absorption systems, fossil clouds of gas from the very early universe, they find an amount that again aligns beautifully with the BBN prediction. It is another check mark, another ringing endorsement of our understanding of the first few minutes. The model works. It consistently and accurately describes the birth of matter. It is a pillar of modern science, a testament to the power of the human mind to reach back across eons and comprehend the mechanics of creation itself. And it is this very success, this overwhelming consistency, that makes the next part of our story so deeply troubling. Because the cosmic recipe includes one more key ingredient, an element just a little heavier than helium. The third element in the periodic table, lithium. Specifically its most common isotope, lithium-7, with 3 protons and 4 neutrons. The same equations, the same single parameter from the cosmic microwave background, the same well-understood laws of nuclear physics that so perfectly predict the amounts of hydrogen, helium and deuterium also make an ironclad prediction for the amount of primordial lithium-7. There is no ambiguity, there is no wiggle room. The theory proclaims exactly how much lithium the Big Bang should have created. And that is where our triumphant story shatters. When we point our telescopes to the heavens to check this final prediction, we find a stark and unnerving discrepancy. We don't find the amount of lithium the theory demands. We find far, far less. To find the primordial abundance of lithium, astronomers must look for the oldest stars in our galaxy. These are the ancient metal-poor stars dwelling in the Milky Way's halo relics from a much earlier cosmic epoch. Their atmospheres are thought to be pristine windows into the past, preserving a nearly uncontaminated sample of the original gas cloud from which they formed. They are the keepers of the cosmic recipe. For decades, astronomers have meticulously measured the chemical composition of these stellar fossils, and they all tell the same defiant story. As they measure stars with lower and lower heavy element content, pushing further and further back into cosmic history, the amount of lithium they observe plateaus. It settles on a consistent value known as the Spite Plateau. This is believed to be the primordial lithium abundance the baseline level created in the Big Bang before any stellar processes could alter it. And this observed value is wrong. It is catastrophically wrong. The amount of lithium-7 we see in these ancient stars is about 1/3 to 1/4 of the amount predicted by our otherwise flawless model of the Big Bang. Let this sink in. It's not a small statistical error. It's not a minor rounding issue. It is a gaping chasm between theory and observation. Imagine following a trusted recipe that calls for 3 cups of a vital ingredient, but when you taste the final product, you can only find evidence of 1 cup. You would not question the existence of the kitchen, or the oven, or the other ingredients. You would become obsessed with that one missing component. Where did it go? Was it ever there to begin with? This is the crisis cosmologists face. The lithium problem is not a fringe anomaly. It is a direct confrontation with the standard model of cosmology. It represents a fundamental conflict between the 2 most precise tools we have for studying the early universe, the physics of Big Bang Nucleosynthesis and our observations of the most ancient stars. The same model that is celebrated for its stunning accuracy with hydrogen and helium fails spectacularly with lithium. It's as if a master composer wrote a perfect symphony, but for one single instrument all the notes are jarringly inexplicably wrong. This isn't just about one element. Lithium's defiance strikes at the heart of our confidence in our cosmic origin story. It forces us to ask terrifyingly fundamental questions. Is our understanding of the nuclear physics that governed the first 3 minutes flawed in some subtle but profound way we have yet to discover? Are the stars themselves, our most trusted witnesses to the ancient universe, misleading us? Could there be some unknown mechanism within these ancient suns that has destroyed their original lithium, hiding the evidence from our spectrographs? Or could the answer be something far more exotic, something that hints at new physics beyond the standard model? Perhaps the decay of an unknown particle in the early universe altered the cosmic abundances. Perhaps the fundamental constants of nature were slightly different during that fiery epoch. Perhaps something about the nature of dark matter, the mysterious substance that makes up most of the universe's mass, influenced the creation of the elements in a way we have never imagined. Each possibility is a doorway into a new and uncharted territory of scientific exploration. The lithium problem has transformed from a nagging numerical discrepancy into a profound clue. It is a loose thread in the magnificent tapestry of the Big Bang. Pulling on it could unravel a small explainable knot, or it could unravel everything we thought we knew. The stakes are immense. Solving this mystery is not merely about balancing a cosmic equation. It is about validating the entire narrative of our universe's birth. It is a scientific detective story of the highest order. The scene of the crime is the first 3 minutes of time. The evidence is encoded in the faint spectral lines of light from stars that are billions of years old, and the list of suspects is as deep and unsettling as the cosmos itself. Is the problem with our witnesses, the ancient stars? Is it with the rulebook, our understanding of nuclear physics? Or is there an unknown perpetrator, a new force or particle of nature still lurking in the shadows of the cosmos? Our investigation begins now. We must interrogate the stars. What if the entire universe, every galaxy, every star, every atom that makes up you and me, was written from a recipe with only 3 ingredients? A recipe followed just once in a frantic flash of creation, setting the cosmic menu for all of time. We look out into a cosmos of staggering complexity, a periodic table filled with 100 different elements each with its own unique properties, building everything from shimmering nebulae to the silent rocky worlds orbiting distant suns. But this elaborate chemical banquet we see today is a recent development. To find the original primordial ingredients, we must journey back beyond the first stars, beyond the formation of galaxies, to a time when the entire observable universe was a place smaller than a single atom and hotter than the core of 1,000 suns. We must return to the first 3 minutes. This is not a journey of speculation or philosophy. It is a journey into the heart of a tested and triumphant theory, a cornerstone of modern cosmology known as Big Bang Nucleosynthesis. It is the story of the universe's first act of creation. After the initial incomprehensible bang, the cosmos was a seething, incandescent fog of pure energy and elementary particles. A quark gluon plasma so dense and hot that the very concepts of matter as we know it simply couldn't exist. But as the universe expanded, it cooled, and in that cooling a critical threshold was crossed. The quarks, the fundamental building blocks of matter, were finally able to cling together, bound by the strongest force in nature. For the first time, the universe had protons and neutrons. Imagine a furnace not of fire and metal, but of space-time itself, a crucible of such immense pressure and temperature that it defies all earthly comparison. Within this primordial forge, these newly formed protons and neutrons, the lonely nuclei of future hydrogen atoms and their neutral counterparts, raced about in a chaotic, brilliant ballet. They were the raw materials, the foundational clay from which everything else would be sculpted. The universe was now a thick, uniform soup of these particles, bathed in a torrent of photons, electrons, and elusive neutrinos. For a fleeting moment, the cosmos was simple, its contents predictable, its destiny hanging on a knife's edge. Because the furnace was cooling fast. An unstoppable expansion was stretching the fabric of reality, thinning out this particle soup and lowering its temperature with every passing microsecond. This created a dramatic cosmic deadline. For nuclear fusion to occur, for these protons and neutrons to stick together and form heavier elements, 2 things were needed: immense heat to overcome the electrical repulsion between protons and incredible density to ensure they collided frequently. Too hot, and any newly formed atomic nucleus would be instantly blasted apart by a high-energy photon. Too cool, and the particles would no longer have enough energy to fuse at all. There was a window, a brief, perfect interval, beginning when the universe was about 1 second old and lasting for only a few minutes. This was the universe's one and only chance to forge its foundational elements on a grand cosmic scale. As the clock started, the most important factor was the delicate ratio of protons to neutrons. In the initial searing heat, they could freely transform into one another, but as the universe cooled below a critical point, the neutrons, being slightly more massive, found it harder to be created. Their numbers became fixed, frozen out, at a ratio of roughly 1 neutron for every 7 protons. This specific ratio, dictated by the fundamental laws of physics, was the master variable that would determine the final composition of the cosmos. The first step in this chain of creation was the most crucial and the most difficult. 2 protons could not simply stick together. Instead, a proton and a neutron had to find each other in the swirling chaos and bind, to form a nucleus of deuterium, or heavy hydrogen. This was the gateway, the essential cosmic keystone. For the first minute or so, the universe was still too hot even for this. Every time a deuterium nucleus formed a powerful photon, would smash into it, shattering the fragile bond. This period is known as the deuterium bottleneck, a cosmic traffic jam that prevented any further creation. The universe was building up a tremendous potential, a seething sea of raw ingredients just waiting for the temperature to drop to the perfect permissive level. Then it happened. The universe cooled just enough. Suddenly, deuterium nuclei could survive the photon storm. The bottleneck was broken, and the floodgates of creation were thrown open. What followed was a chain reaction of breathtaking speed and efficiency. Once deuterium existed, it was immediately consumed. A deuterium nucleus would collide with another proton, creating a light isotope of helium called helium-3, or it would collide with a neutron forming tritium. and these new heavier nuclei were themselves immediately swept up in the ongoing fury of fusion. The ultimate prize in this frantic dance was the formation of helium-4, a nucleus of 2 protons and 2 neutrons. Helium-4 is a marvel of nuclear stability. Its components are bound together with such immense force that it represents a kind of gravitational cul-de-sac for light elements. Once formed, it is incredibly difficult to break apart or to fuse into anything heavier under these conditions. It is a cosmic lockbox, a finished product. So as soon as the deuterium bottleneck cleared, virtually all of the available neutrons were instantly swept up and locked away into the unassailable fortress of helium-4 nuclei. This process was so ferociously efficient that it consumed the ingredients almost as fast as they became available. In a span of minutes, about a quarter of the entire mass of the ordinary matter in the universe was converted from simple protons into stable, enduring helium. This is a profound realization. Look up at the night sky. Every star you see, including our own sun, is a nuclear furnace, and for billions of years they have been laboriously fusing hydrogen into helium. Yet all of that stellar work combined accounts for only a tiny fraction of the helium in the cosmos. The overwhelming majority of it, the vast cosmic ocean of helium in which galaxies swim, was forged not in stars but right here, in these first few frantic minutes. The theory of Big Bang Nucleosynthesis predicted that the early universe should be composed of roughly 75% hydrogen and 25% helium by mass. This wasn't a guess. It was a direct calculation based on the neutron-to-proton ratio, a number that flowed directly from the laws of physics. But hydrogen and helium were not the only products of this primordial fire. The story has one more character, a faint and mysterious player created on the absolute margins of the main event. In the cosmic crucible amid the rampant formation of helium, a few other far rarer reactions could occur. A helium-4 nucleus might collide with a tritium nucleus. A different helium-4 nucleus might collide with helium-3. These rare high-energy encounters could just occasionally produce a stable nucleus with 7 particles, 3 protons and 4 neutrons. This was lithium-7. Another pathway involved the fusion of 2 helium nuclei to form an unstable isotope of beryllium, which would also, after capturing a neutron or proton, lead to the same result. Lithium was a cosmic afterthought. For every billion protons in the early universe, the raging furnace of the Big Bang produced 100 million helium nuclei, but only a handful of lithium atoms. Why so few? The answer lies in a fundamental quirk of nuclear physics. There is no stable atom with 5 or 8 nuclear particles. This creates a mass gap, a broken rung on the ladder of element creation. Fusing a helium-4 nucleus with a proton gives you an unstable mass 5 nucleus that immediately falls apart. Fusing 2 helium-4 nuclei gives you an unstable mass 8 nucleus that does the same. This bottleneck made it extraordinarily difficult for the early universe to build anything heavier than helium. Lithium was the last gasp of the primordial forge. It was the heaviest element created in any significant quantity before the furnace finally went cold. As the universe continued its relentless expansion, the density and temperature dropped below the threshold for fusion. The particles grew too far apart, their energies too low. The window of opportunity opened for mere minutes slammed shut. The frantic era of Big Bang nucleosynthesis was over. The cosmic recipe was set. The primordial composition of the universe was frozen in place, a vast sea of hydrogen, a substantial ocean of helium, and locked within it like a single grain of sand on an endless beach, a tiny, exquisitely precise amount of lithium. For decades, this beautiful, elegant theory remained just that, a theory. An idea born from physics and mathematics describing a moment no one could ever witness. How could we possibly test it? How can you measure the composition of the universe from 13.8 billion years ago? The cosmos we see today is contaminated. Generations of stars have lived and died cooking up heavier elements, carbon, oxygen, iron in their cores, and scattering them throughout space in violent supernova explosions. Looking at a modern star or galaxy to find the primordial mix would be like trying to discover the original chemical composition of Earth's oceans by analysing a sample from a polluted harbour. The original signal would be lost, drowned out by billions of years of cosmic industry. To verify the predictions of Big Bang nucleosynthesis, we needed a time machine. We needed to find a way to analyse matter that was as pristine and untouched as possible. And astronomers, with their characteristic ingenuity, found two. The first involves a form of cosmic archaeology. We search for the oldest, most ancient stars in our own galaxy. These are the survivors from a much earlier epoch, relics born when the universe was still young. Known as population 2 stars, they are profoundly metal-poor, an astronomical term meaning they are composed almost entirely of the hydrogen and helium forged in the Big Bang. They contain only the faintest trace of the heavier elements cooked up by an even earlier, now extinct generation of stars. Finding these stars is a monumental challenge. They are often faint and hidden within the vast halo of our Milky Way. But when we find one, we can perform a remarkable act of remote analysis. By capturing its light and splitting it into a spectrum, a rainbow of colours, we can see dark lines, gaps in the light. These absorption lines are atomic fingerprints. Each element in the star's atmosphere absorbs light at very specific frequencies, leaving a unique identifiable barcode in its spectrum. By carefully measuring the strength of these lines, we can deduce the exact chemical composition of the star's outer layers, a pristine sample of the gas cloud from which it formed billions of years ago. We are in effect reading a fossilized record of the early universe. Our second time machine allows us to look even further back to a time before most stars had even formed. We use the universe's most powerful beacons, quasars. These are the brilliantly luminous cores of distant infant galaxies powered by supermassive black holes feeding on enormous quantities of gas. A quasar's light is so incredibly bright that it can travel across almost the entire observable universe to reach our telescopes. On its multi-billion-year journey, that light passes through vast intervening clouds of intergalactic gas. These clouds are true relics of the dawn, enormous reservoirs of matter that have never been pulled into a galaxy, never been processed by a star. They are arguably the most pristine samples of the universe's original material we can ever hope to find. Just as with the stars, these clouds leave their fingerprints on the quasar's light. As the beam passes through the hydrogen-helium and lithium atoms in the cloud, absorb their characteristic frequencies, etching a faint set of absorption lines into the quasar's spectrum. Decoding these incredibly faint signals from the edge of observable reality is one of the great technical triumphs of modern astrophysics. It is like trying to determine the composition of a fog bank 1,000 miles away by analysing the subtle colour changes in a lighthouse beam shining through it. Yet we can do it, and by doing so we gain a second completely independent measurement of the universe's primordial composition. Across decades of painstaking observations using both ancient stars and distant gas clouds, the results came in, and they were spectacular. The measurements for the primordial abundance of hydrogen and deuterium were a perfect match for the predictions of the theory, and the measurement for helium-4 that roughly 25% of the universe's mass should be helium was stunningly, breathtakingly accurate. It was a resounding triumph. It confirmed that we truly understood the physics of the universe when it was only a few minutes old. Big Bang Nucleosynthesis became a pillar of modern cosmology, a testament to the power of the scientific method to reach back and comprehend the very beginning of time itself. With the success of hydrogen and helium, cosmologists turned their attention to that final trace ingredient, lithium. The same physics, the same model that had so perfectly predicted the other elements, could be used to calculate the precise amount of lithium that the Big Bang must have created. This prediction wasn't loose or approximate. Thanks to incredibly precise measurements of the early universe from our observations of the cosmic microwave background radiation, we know the density of ordinary matter with astonishing accuracy. Plugging this number into the equations of Big Bang nucleosynthesis doesn't yield a range of possibilities for lithium. It yields a single, concrete, unshakable number. The theory makes a specific, non-negotiable prediction. It tells us with a high degree of certainty exactly how much lithium should be etched into the atmospheres of those ancient stars and hidden in those distant gas clouds. It is the third and final test of the entire model, the capstone on a magnificent intellectual edifice. A number etched into the very fabric of the cosmos by the fire of its birth. This should have been our final glorious confirmation, the moment when theory and observation locked into perfect harmonious agreement. But what if when we finally added up all the evidence and looked at that number with unforgiving clarity, it wasn't there? What if the universe was hiding a secret, a profound discrepancy concealed within its lightest and most fragile element. And so, with the cosmic abundances of hydrogen and its heavier isotope deuterium, we found a universe behaving exactly as our theories predicted it should. The ancient gas clouds, scattered like smoke from a cosmic fire, held the precise chemical signature of that first furious creation. Helium, the second most abundant element, fell into line with breathtaking accuracy, a testament to the power of our understanding, a triumph of theoretical cosmology. For decades, Big Bang Nucleosynthesis stood as an almost perfect pillar, one of the great intellectual achievements of our species. We had it seem deciphered, the universe's own birth certificate, and every line, every word appeared to be in its proper place. Except for one. A single, nagging inconsistency, a number that simply would not fit, a quiet, disquieting detail that at first seemed like a minor rounding error, a problem that would surely resolve itself with better telescopes or more precise calculations. It was a smudge on an otherwise pristine document, a dissonant chord in what should have been a perfect cosmic symphony. This was the problem of lithium. The third element on the periodic table, forged in the smallest quantities, was about to present cosmology with its most stubborn and perplexing challenge. To confront it, we first had to be certain it was real. The task required a two-pronged assault, an unflinching investigation into both the heavens above and the fundamental laws of physics here on Earth. One community of scientists would need to prove what the universe is, while another would have to prove what it must be here. The confrontation began in the quiet solitude of the world's great observatories, pointed towards the most ancient residents of our own Milky Way galaxy. To find primordial lithium, you must find a place untouched by the modern cosmos. You need a time capsule, a relic from an epoch before the great stellar forges began their work of churning out carbon, oxygen, and iron. You must hunt for the galaxy's firstborn stars. These are the so-called Population 2 stars, ancient metal-poor suns that wander the vast, lonely halo of the Milky Way. They are profoundly old, formed from the nearly pure hydrogen and helium gas clouds that condensed in the aftermath of the Big Bang itself. Their atmospheres are living museums preserving the chemical inventory of the universe, as it was more than 13 billion years ago. Finding them is a challenge. They are faint, distant, and scattered across the sky. But for astronomers, they are the Rosetta Stone for understanding our cosmic origins. The technique they use is one of the most powerful tools in science spectroscopy. By capturing the faint light from one of these halo stars and passing it through a prism, astronomers can spread it out into a rainbow of its constituent colours, a spectrum. Imprinted upon this spectrum are dark, impossibly thin lines, like a cosmic barcode unique to that star. Each line corresponds to a specific element in the star's atmosphere, an element absorbing a very particular wavelength of light as it escapes into space. The depth and darkness of that line tells you not just that the element is there, but precisely how much of it there is. It is a painstaking, almost miraculous form of remote chemical analysis conducted across gulfs of space and time that stagger the imagination. In the late 1970s and early 1980s, two French astronomers, François and Monique Spite, began a systematic survey of these ancient stars. They were looking for clues about the early galaxy, but they found something far stranger. As they analysed star after star, a bizarre and unexpected pattern began to emerge. When they measured the amount of lithium they found, it was remarkably, almost impossibly constant. Star after star, regardless of its temperature or its precise location in the galactic halo, showed the exact same lithium abundance. It was as if every single one of these ancient objects had been born with a universally mandated fixed inheritance of the element. This discovery, which came to be known as the Spite Plateau, was a revelation. The sheer uniformity of it was a stunning clue. It strongly suggested that this lithium wasn't created in the stars themselves. If it had been, the amount would vary wildly depending on the star's mass and evolution. No, this looked primordial. This looked like the baseline, the floor value of lithium baked into the universe at its birth. We were for the first time staring directly at the lithium forged in the Big Bang. And here the confrontation truly began. Because the number they measured the value of this primordial plateau was not the number our theories had predicted. It wasn't even close. Our model of the Big Bang, the very same standard model that had so flawlessly predicted the abundances of deuterium and helium, was unequivocal. It provided a clear, firm prediction for primordial lithium. Yet the ancient stars were telling a different story. They were whispering a number that was significantly lower. The first measurement suggested the reality was about half of the prediction. It was a troubling gap, but perhaps it was an error. Maybe the physics of stellar atmospheres was more complex than we appreciated. Maybe our understanding of spectroscopy had a subtle flaw. So began the forensic audit of the skies. For the next 4 decades, astronomers did what scientists do best. They tried, with every tool and technique at their disposal, to prove themselves wrong. They refined their models of how stars absorb light, accounting for convection turbulence and magnetic fields with ever greater sophistication. They built bigger telescopes with more sensitive spectrographs, capable of dissecting starlight with unprecedented precision. They hunted for even older, even more metal-poor stars, pushing further back into the cosmic dawn to find the purest possible relics. Team after team, observatory after observatory across the globe repeated the measurements, cross-checked the data, and challenged every assumption. And with every new observation, every refinement in technique, the problem did not go away. It got worse. The gap between prediction and observation didn't shrink, it widened. The observational data solidified, becoming an incontrovertible wall of evidence. The spite plateau was real. The number it represented was unshakable, and it was stubbornly, defiantly, almost maliciously a factor of 3 lower than what the standard model of the Big Bang demanded. Imagine building the most beautiful, intricate clockwork mechanism. Every gear is perfectly machined, every spring calibrated. It correctly predicts the hours, the minutes, the seasons, the turning of the planets. It works perfectly. Except for one small hand which consistently runs 3 times too slow. You would not throw the whole clock away. You would become obsessed with that one single gear. This was the obsession that gripped the other side of the investigation, the nuclear physicists and the theorists. While astronomers interrogated the stars, this second community turned its gaze inward to the subatomic realm, to the very engine of BBN itself. Their working hypothesis was simple and humbling. The mistake must be in our physics. Our calculation of what the universe must be had to be flawed. The standard model of Big Bang Nucleosynthesis is not just an idea. It is a sprawling complex network of interlocking nuclear reactions. It is a computer simulation that begins with a sea of protons and neutrons in a rapidly expanding cooling universe. It follows second by second how these particles collide, fuse and decay. There are 12 primary reactions that govern the production and destruction of the light elements in those first few minutes. The outcome, the final abundance of deuterium, helium and lithium, depends exquisitely on the precise rates of these 12 reactions. And it's these rates known as cross-sections that became the prime suspects. A cross-section is in essence the measure of probability. What is the likelihood that a proton flying through the primordial plasma at a certain energy will successfully fuse with a nucleus of beryllium-7? What is the chance it will instead scatter off or trigger a different reaction? These probabilities are not guessed. They are measured painstakingly in laboratories on Earth. Scientists use particle accelerators as surrogate Big Bangs. They create beams of protons, neutrons, and light nuclei, and they smash them into targets, meticulously counting the results. It is incredibly difficult work. You are trying to replicate the hellish conditions of the first 3 minutes temperatures of 1 billion degrees, incredible densities within the confines of a detector. You're trying to measure reactions that are sometimes fantastically rare. With the lithium problem looming over them, nuclear physics laboratories around the world launched a new campaign to remeasure every single one of those 12 critical reactions. They focused especially on the pathways that create and, more importantly, destroy lithium. The dominant production route for primordial lithium-7 isn't direct. It's a 2-step process. First, 2 different types of helium nuclei fuse to form an unstable isotope, beryllium-7. Then, much later, once the universe has cooled, this beryllium-7 captures an electron and decays into the stable lithium-7 that we see today. So the central mystery became, could there be an unknown or underestimated way to destroy this parent beryllium-7 before it has a chance to decay? Physicists scoured their data for a backdoor reaction, a cosmic leak that could siphon off the beryllium and thus suppress the final lithium abundance. They fired protons at beryllium targets. They fired neutrons. They fired deuterium. They tried every plausible interaction, pushing their accelerators to new levels of precision. They refined their measurements of the half-life of beryllium itself. They ran supercomputer simulations modelling the plasma physics in more detail than ever before. Every new experiment, every more powerful simulation was freighted with expectation. Perhaps this next run would reveal the missing cross-section. Perhaps this would be the discovery that made the numbers line up, that would fix the dissonant chord and restore harmony to the cosmic model. But the universe refused to cooperate. The laboratory results that came back were in their own way as frustratingly consistent as the astronomical observations from the mountaintop telescopes. The old measurements, it turned out, were remarkably good. The new higher precision experiments largely confirmed them. They tweaked the numbers, narrowing the error bars, but the central values held firm. There was no undiscovered high probability reaction channel that could destroy beryllium at the rate required. There was no gaping hole in our understanding of nuclear physics at these energies. The standard network of reactions was solid. It was robust. The physicists had, with heroic effort, slammed the door on any easy explanation. The error was not in their particle accelerators, just as it was not in the astronomers' telescopes. So here we stand at the end of this grand confrontation. Two vast, independent and meticulous lines of scientific inquiry pursued for decades by thousands of brilliant and dedicated minds have converged on an impossible conclusion. On one side, we have the observers who have read the story written in the light of ancient stars. Their evidence is clear. The amount of primordial lithium in the universe is a specific low value. The data is unyielding, confirmed by telescope after telescope. This is what our universe is. On the other side, we have the theorists and the experimentalists. They have combined Einstein's theory of general relativity with the standard model of particle physics, tested and confirmed in our greatest laboratories. Their prediction is equally clear. The Big Bang must have created 3 times that amount of lithium. This is what our universe must be. The chasm between these two statements is now deep, wide, and terrifyingly real. This is no longer a simple discrepancy. It is not an observational anomaly or a theoretical oversight that can be patched up with a minor tweak. It is a fundamental tension that strikes at the very heart of our cosmic story. The pillar of Big Bang Nucleosynthesis, once thought to be flawless, now bears a deep and undeniable fracture. Every easy answer has been exhausted. Every conventional explanation has failed. We have checked our work and we have checked it again. The math is correct. The observations are correct. Yet they tell 2 different mutually exclusive stories about the dawn of time. We are left with a profound and unsettling silence, the silence that falls when 2 impeccable lines of evidence lead to a logical contradiction. It forces us to ask a question that is both exhilarating and deeply frightening. If there is no error in our instruments or our calculations, then is there an error in our understanding of the universe itself? Something essential, something fundamental about the first few minutes of existence is wrong, and finding out what that is has become one of the most urgent quests in all of science. For decades, the discrepancy was treated not as a crisis, but as a temporary inconvenience. It was a smudge on the otherwise pristine window of cosmology, a stubborn footnote in the grand story of our universe that most believed would eventually be erased by better data or a cleverer calculation. The assumption, a deeply ingrained and perfectly reasonable one, was that we had simply made a mistake. We the observers must have misinterpreted the faint whispers from those ancient stars, or we the theorists must have overlooked some subtle nuance in the furious alchemy of the first 3 minutes. The universe, we were certain, could not be so fundamentally contradictory. It was this quiet confidence in our own fallibility that allowed the lithium problem to fester, to grow from a minor academic puzzle into a profound and unsettling paradox. The first line of defense the first suspect brought in for interrogation was naturally the evidence itself, the measured abundance of lithium in the universe's oldest stellar relics. You can imagine the scene repeated in observatories from the high deserts of Chile to the volcanic peaks of Hawaii. A team of astronomers huddled in the dim glow of computer screens targeting a single, impossibly faint star. This star is no brilliant beacon like our own sun. It is a ghost from a bygone era, a member of the Milky Way's sprawling spherical halo. These are the primordial ones, the survivor stars born when the cosmos was less than 1 billion years old, from gas clouds barely seasoned with the ash of the very first stellar generation. Their chemistry is a time capsule, preserving an almost pure sample of the material forged in the Big Bang. To pry open that capsule is an act of supreme delicacy. For nights on end, the unblinking eye of a giant telescope would stare, gathering the star's feeble light photon by photon. This light, having journeyed across unimaginable voids for over 13 billion years, holds a secret encoded in its very spectrum. Passed through the precise optics of a spectrograph, it is shattered into a rainbow, a celestial barcode of breathtaking complexity. Across this band of colours are thousands of dark, thin lines, a forest of shadows. Each line, known as an absorption feature, marks a specific element in the star's atmosphere, a chemical fingerprint left by atoms absorbing light at their unique characteristic frequencies. Finding the fingerprint of lithium is like trying to find a single specific needle in a cosmic haystack of needles. The signature of lithium-7 is a subtle dip, a fragile notch in the spectrum at a wavelength of 670.8 nanometers. It is faint, easily confused with other spectral features, and notoriously difficult to measure with confidence. This is where the Inquisition began. Could the measurements simply be wrong? Was this whole affair just a case of instrumental error of astronomers squinting at noisy data and seeing a deficit that wasn't truly there? For years, this was the prevailing hope. Rival teams set out to prove each other wrong, a classic and essential feature of the scientific method. They used different telescopes, different spectrographs, and different analytical techniques, each attempting to find the flaw in the previous team's work. They refined their methods for filtering out the noise, for accounting for the blurring effects of the Earth's own turbulent atmosphere. Yet as the years turned into decades, a frustrating consensus began to emerge. The data held firm. From the Very Large Telescope in Chile to the Keck Observatory in Hawaii, the results were unnervingly consistent. Star after ancient star told the same story. They all possessed lithium, but they all possessed roughly 3 to 4 times less than the theory of the Big Bang so confidently predicted. The measurements were not a mistake. This observational bedrock, which came to be known as the Spite Plateau, was real. The name itself, coined by French astronomers Monique and François Spite, who discovered it, hints at the constancy of the finding. Across a wide range of these ancient metal-poor stars, the amount of lithium was stubbornly, inexplicably flat. It simply refused to climb to the level demanded by our cosmological models. But finding the spectral line is only the first step. The true challenge and the next target for intense scrutiny was the interpretation. How do you translate the depth and width of that dark line into a definitive number of lithium atoms? This requires building a sophisticated model of the star itself, a virtual stellar atmosphere inside a supercomputer. You have to know its temperature with exquisite precision. You must understand the turbulence of its outer layers, the convective currents that churn its plasma. You have to account for the way atoms interact, how they are jostled and ionized in that fiery environment. Each of these physical parameters could in principle alter how the lithium signature is imprinted on the starlight. For years, scientists probed these models for a weakness, a hidden lever they could pull to make the observed lithium abundance rise. Could the stars be hotter than we thought? A hotter atmosphere would ionize more lithium, making it invisible to the spectrograph and tricking us into thinking there was less of it. So they refined their stellar thermometers using different spectral lines, from elements like iron and hydrogen as crosschecks. The temperatures were confirmed. Could there be some unknown physical process in the stellar plasma that was masking the lithium? Teams of atomic physicists went back to their laboratories, meticulously remeasuring the properties of lithium atoms under stellar conditions. The physics held up. Could the one-dimensional models of stellar atmospheres be too simple? Perhaps the complex three-dimensional reality of a boiling convective star was the missing piece. So they built vastly more complex 3D models consuming millions of hours of supercomputer time to simulate the surfaces of these ancient suns with breathtaking fidelity. The result of this monumental effort was a scientific dead end. The new, more sophisticated models only reinforced the original conclusion. They tweaked the numbers, slightly narrowing the error bars and increasing the confidence, but they did not bridge the gap. In fact, they made the problem worse. They removed the wiggle room, they slammed shut the escape hatches. The community was forced to confront a chilling realization the observations were not the source of the problem. The amount of lithium we see in these stellar fossils is a hard empirical fact. The universe was telling us through its oldest light that the ledger of primordial elements was short on lithium. The evidence gathered at great expense and with painstaking care over a generation of scientific careers had been cross-examined to the point of exhaustion. It was robust, it was real, and it was profoundly stubbornly wrong. With the observational evidence standing like an unassailable fortress, the scientific community turned its full unsparing attention to the other side of the equation, the theoretical prediction itself. If the measurement of the universe was correct, then perhaps the model we were measuring it against was flawed. This was an even more terrifying prospect. The theory in question was not some fringe hypothesis or a minor addendum to our understanding. It was Big Bang Nucleosynthesis, or BBN, one of the foundational pillars of modern cosmology. BBN is our detailed minute-by-minute account of the cosmic dawn, the story of how the universe in a crucible of unimaginable heat and density forged the first atomic nuclei. It is a theory of spectacular predictive power, a triumph of nuclear physics and general relativity working in perfect concert. To question BBN is not to question a single calculation. It is to question our entire timeline of the early universe. The theory's success had been legendary. It had correctly predicted the vast abundance of hydrogen and the roughly 25% of cosmic matter that should be helium. It had even correctly predicted the trace amounts of deuterium or heavy hydrogen, an isotope so fragile it can only have been created in the Big Bang's unique conditions and is easily destroyed inside stars. The BBN predictions for hydrogen, helium and deuterium match our observations of the universe with stunning, breathtaking precision. They are considered cornerstone proofs of the Big Bang theory itself. They are the receipts from the universe's creation, and 3 of the 4 items on the list match perfectly. Only lithium, the final entry, is wrong. For a time, the hope was that the input parameters for the BBN calculation were slightly off. The entire theoretical edifice of BBN rests on one crucial measured number, the cosmic baryon to photon ratio. This is in essence a measure of the density of normal matter, the stuff that makes up you, me and the stars in the early universe. For a long time, this number had some uncertainty, a bit of fuzziness that provided theorists with a convenient space in which to solve the lithium problem. By tweaking this density within its accepted error bars, they could try to force the theoretical prediction for lithium down to match the observed value. It felt like a plausible escape route. If the density of matter was slightly different than we thought, perhaps the cosmic nuclear reactor would have produced less lithium. It was a reasonable conservative hypothesis. But then in the early 21st century, that escape route was sealed off completely and irrevocably. A new source of information arrived, a messenger from an even earlier epoch of cosmic history. Satellites like NASA's Wilkinson Microwave Anisotropy Probe, or WMAP, and later the European Space Agency's Planck satellite, gave us our first ultra-high-resolution baby picture of the universe. They mapped the cosmic microwave background, the faint afterglow of the Big Bang, with a precision that was once the stuff of science fiction. This fossil light released when the universe was just 380,000 years old is not uniform. It is dappled with tiny, almost imperceptible fluctuations in temperature hot and cold spots that represent the seeds of all future structures, including the galaxies themselves. The statistical pattern of these spots, the specific way they are distributed across the sky, is a cosmological Rosetta Stone. Encoded within it are the fundamental parameters of our universe, its age, its geometry, and most critically for our story, the precise density of baryonic matter. The Planck satellite in particular pinned down the baryon to photon ratio with an incredible razor-thin margin of error of less than 1%. It was one of the most precise measurements in all of science, and when cosmologists took this new hyper-accurate number and plugged it back into the equations of Big Bang nucleosynthesis, the result sent a shockwave through the field. There was no longer any wiggle room. The uncertainty was gone. The new high-precision BBN calculation, anchored by the godlike data from the CMB, didn't just predict the abundance of lithium, it predicted it with unwavering mathematical certainty. The theory, now more constrained and more powerful than ever before, doubled down. It confirmed that the universe should have produced 3 to 4 times more lithium-7 than the oldest stars contain. The conflict was no longer a vague disagreement between a fuzzy prediction and a noisy measurement. It had sharpened into a high-fidelity 5 sigma contradiction between two of our most trusted and precise views of the cosmos. On one hand, you had the direct archaeological evidence from the first stars. On the other, you had a powerful theoretical prediction, now independently verified and calibrated by the universe's own initial conditions. Both were exquisitely precise, and both were in violent opposition. This was the moment of crisis. This was the turning point when the lithium problem transformed from a nagging annoyance into a potential revolution. The community had to accept that there were no easy outs. They had exhausted the obvious explanations. The stellar observers had done their job flawlessly. The cosmologists armed with CMB data had refined their model to a point of near perfection. The nuclear physicists who supply the reaction rates for the BBN code had remeasured and rechecked every single interaction in their particle accelerators. No one was at fault. The data was solid. The theory was sound. The math was correct. The inescapable conclusion was that something was fundamentally wrong, not with our methods, but with our understanding. We stood at a precipice staring into a chasm that had opened up in the very foundations of our physical reality. The robustness of the problem had cornered us, forcing us to confront possibilities that were once unthinkable. It presented a stark binary choice. Either there is a profound flaw in our story of the cosmos, the Big Bang model itself, a model that has been spectacularly successful in every other conceivable test, or the flaw lies in the rulebook the universe uses to play the game, the standard model of particle physics. This is the collection of theories that describes all the known fundamental forces and particles. The BBN calculation assumes that the standard model is the complete and final word on particle physics. But what if it isn't? What if during that first fiery inferno there were other particles, other forces at play that we have not yet discovered? This is a ghost in the machine, a whisper of physics beyond the known, a hint that the laws we have so carefully pieced together here on Earth might not be the whole story. The stubborn refusal of lithium to align with our predictions is more than just a numerical error. It is a challenge. It is the universe leaving a deliberate, tantalizing clue, a loose thread that if pulled could unravel our most cherished theories of existence. We had arrived at a point of profound intellectual humility. After decades of relentless effort, we had not solved the problem. We had only succeeded in proving just how deep, how real, and how incredibly significant it truly is. The age of simple explanations was over. The search for a solution would now have to take us far beyond the familiar shores of established science into the wild and speculative waters of new physics, and so we are left here adrift in a cosmic contradiction. The blueprint of the Big Bang, written in the light of the most ancient observable phenomenon, the cosmic microwave background, gives us a number for lithium, an unambiguous, confident prediction. Yet the oldest stars, the most pristine relics of that early cosmos, tell a different story, whispering a number 3 times smaller. This isn't a rounding error, it is a chasm, a fundamental disagreement between our most powerful theory of cosmic origins and our direct observations of its consequences. The pillar of prediction and the pillar of observation, which should form a triumphant arch, instead stand apart with a void of bewilderment between them. Faced with such an intractable puzzle, science does what it has always done. It splits its forces, sending out search parties down 2 profoundly different and dangerous paths. One path leads downward into the fiery hearts of the very stars we are measuring, a search for a culprit within the known laws of astrophysics. The other path leads outward into the wild, unmapped territory of theoretical physics, a hunt for ghosts in the machinery of the universe itself. Let us first take the downward path, the more conservative of the two, for it is always prudent to question the scene of the crime before you question the laws of the land. The central premise is deceptively simple. Perhaps the lithium was there all along in the exact amount predicted by the Big Bang. Perhaps the primordial gas clouds from which these ancient stars were born were indeed enriched with the correct cosmic recipe. But if that is true, then the stars themselves must be the culprits. They must be cosmic furnaces that are far more efficient at destroying this fragile element than our models have ever accounted for. This is a search for a hidden stellar process, a secret mechanism of destruction happening deep within these population 2 giants. The primary suspect is a process known as convection. Imagine the star as a boiling pot of water. Hot plasma from the deep interior rises, cools at the surface, and then sinks again, creating a vast slow-motion circulatory system. We have long known that lithium is a delicate nucleus. It cannot withstand the ferocious temperatures of a star's core. If it gets dragged down too deep below about 2.5 million degrees Kelvin, it is instantly annihilated, torn apart by collisions with protons. For decades, astrophysicists believed the lithium in these specific old metal-poor stars was safe. Our standard models showed that their outer layers, their atmospheres where we take our measurements, should be stable and serene. Their convective zones were thought to be exceptionally shallow, a thin, churning layer that never reached the devastating temperatures of the stellar depths. The surface lithium we thought was quarantined, preserved as a perfect fossil of the Big Bang. But what if this picture is wrong? What if there is another more subtle transport mechanism at play, a hidden current that dredges the surface material down into the inferno? This is where the investigation becomes fantastically complex because we cannot see inside a star. We are like detectives trying to map the hidden passageways of a fortress from the outside, relying on inference and theory. Scientists have proposed a rogues gallery of potential transport mechanisms. Perhaps the rotation of the star, even if slow, induces a gentle but persistent mixing that our models miss. A star isn't a solid, rigid body. It spins differentially faster at the equator, slower at the poles, creating shears and turbulence that could slowly, over billions of years, cycle lithium down to its doom. Another possibility involves something called internal gravity waves, not the gravitational waves of colliding black holes, but ripples of stellar plasma that propagate through the interior. Much like waves on an ocean, these could carry energy and momentum, potentially driving a slow, deep circulation that standard models overlook. Each of these ideas presents a formidable challenge to astrophysicists. Modelling the three-dimensional turbulent magnetized plasma inside a star is one of the most difficult computational problems in all of science. Our current models are brilliant but imperfect approximations, often relying on simplified parameters, what some might uncharitably call fudge factors, to describe complex phenomena like convection and turbulence. Is the solution to the lithium problem buried within the limitations of our own computer codes? Are we simply missing a crucial piece of physics in our simulations of how stars live and breathe? It's a humbling thought that the grand cosmic mystery might resolve into a subtle correction in the equations governing stellar hydrodynamics. Yet this conservative path has a formidable obstacle of its own, an observation that stubbornly resists easy explanation. When astronomers measure the lithium content across hundreds of these ancient stars, they find something astonishing, something that argues against the idea of stellar destruction. They find a plateau. It's called the Spite Plateau, named for the astronomers who first characterized it. Regardless of a star's surface temperature or its precise, minuscule metal content, they all seem to have almost exactly the same amount of lithium, this same depleted factor of 3 too low amount. This uniformity is deeply puzzling. If stars were destroying lithium through complex internal processes like rotation and turbulence, you would expect those processes to vary from star to star. One star might spin a little faster, another might have a slightly different internal structure. Surely these differences would lead to different rates of lithium destruction. Instead of a flat plateau, we should see a scattered mess, a shotgun blast of data points, where some stars have burned much of their lithium and others have preserved more, but we don't. We see this unnervingly consistent flat line. It looks less like the messy result of chaotic stellar processes and more like a primordial foundational flaw. It's as if these stars were all born from a gas that already had this specific lower amount of lithium baked in. The Spite Plateau, for all its mystery, seems to be telling us that the lithium level was set before the stars ever formed, shifting the blame away from stellar interiors and back toward the cosmos at large. This forces the investigators on the astrophysical path to look for culprits beyond the stars themselves in the interstellar medium of the infant universe. Could something have happened to the lithium in the vast cold darkness between its creation in the Big Bang and its incorporation into the first stars? One speculative idea points to the universe's very first stellar explosions. The first generation of stars, the mythical population 3, were gargantuan beasts hundreds of times more massive than our Sun. They lived fast and died young in cataclysmic supernovae seeding the cosmos with the first heavy elements. These explosions would have also unleashed torrents of high-energy cosmic rays. It is conceivable that these primordial cosmic rays could have acted as celestial saboteurs slamming into the fragile Lithium-7 nuclei floating in the interstellar gas, and splitting them apart, a process known as spallation. This could have selectively reduced the universe's lithium inventory before the next generation of stars, the ones we can actually observe, ever began to form. However, this scenario requires a very fine-tuned and intense flux of cosmic rays in the early universe, more than is typically assumed, and provides no easy way to verify. It remains a fringe but tantalizing possibility. And so, after exhausting the avenues within our known physics of stars and galaxies, the first search party returns with troubling news. The evidence is contradictory. The clues are faint. The culprit, if it exists within the realm of conventional astrophysics, is a master of disguise, leaving behind a scene so clean it almost seems unnatural. This is the moment the investigation takes a turn toward the profound, the unsettling, the heretical. If we cannot find a mundane explanation for the missing lithium, we are forced to confront a far more radical possibility that there is nothing wrong with the stars and there is nothing wrong with our observations. The error may lie in the rulebook itself. We must now walk the second path into the speculative wilderness of new physics. This path requires us to question the very foundations of our cosmic understanding, to entertain the notion that the Big Bang was not quite the event we imagine it to be. It suggests that in those first few minutes the universe was haunted by entities and governed by forces that are not part of our vaunted standard model of particle physics. This is not a step taken lightly. The Standard Model is the most successful scientific theory ever devised, a triumphant description of the fundamental particles and forces that build our reality. To suggest it is incomplete is to suggest there are ghosts in the machine whispers of a deeper, stranger reality we have yet to grasp. The first suspect in this new investigation is a phantom particle, a ghost from the dark side of the universe. We know that most of the matter in the cosmos is not the familiar stuff of atoms and stars, but an invisible, enigmatic substance we call dark matter. Our Standard Model has no place for it. It is by definition new physics. What if this dark matter is not perfectly stable? Imagine a hypothetical heavy dark matter particle created in the searing heat of the Big Bang that is unstable. Let's say it has a lifetime of just a few minutes, long enough to survive past the initial creation of helium and deuterium, but short enough to decay right when lithium is being formed. When this particle decays, it could release a shower of high-energy photons or other exotic particles into the primordial plasma. These energetic projectiles would act like a cosmic blowtorch, seeking out and destroying the delicate nuclei of beryllium-7, the immediate progenitor of most lithium-7. The beauty of this idea is its precision. Beryllium-7 is more fragile than the tightly bound nuclei of deuterium and helium-4. Therefore, a carefully tuned decay could selectively blast apart the beryllium-7, drastically reducing the amount of lithium that ultimately forms, while leaving the triumphant predictions for deuterium and helium almost completely unscathed. It solves the problem with surgical accuracy. But its elegance is also its greatest weakness. This particle is an invention a phantom conjured for the express purpose of solving this one specific problem. It is what scientists call an ad hoc hypothesis. We have no other evidence that such a particle ever existed. It has not appeared in any other cosmological observation or particle accelerator experiment. To believe in it is to believe in a ghost that appeared for a few minutes at the dawn of time, committed a single act of cosmic sabotage, and then vanished forever without a trace. Science demands more. It demands corroborating evidence, a fingerprint left elsewhere at the scene. Without it, the decaying dark matter particle remains a compelling but ultimately unsatisfying ghost story. This search for spectral evidence leads us to an even grander and more ambitious theory: supersymmetry, or SUSY. For decades, it was the leading candidate for physics beyond the Standard Model. Supersymmetry postulates a profound and elegant symmetry in nature, suggesting that for every fundamental particle we know, there exists a heavier superpartner. The electron has the selectron, the photon has the photino, and so on. In many supersymmetric models, the lightest of these superpartners is a stable heavy particle, a perfect candidate for dark matter. And it's here that a new potential culprit for the lithium problem emerges. In the hot, dense soup of the early universe, these supersymmetric particles would have been abundant. One of them, the neutralino, could have acted as a cosmic catalyst for destruction. The proposed mechanism is subtle and ingenious. A neutralino could temporarily bind with a nucleus of beryllium-7. This fleeting exotic state would create a brand new unexpected pathway for the beryllium-7 to be destroyed by a passing proton, a pathway that simply doesn't exist in standard Big Bang nucleosynthesis. It's like a saboteur providing a secret key that allows an enemy agent into the fortress. The neutralino facilitates the destruction and then moves on unscathed to the next unsuspecting nucleus. Once again, this solution is remarkably precise. It targets the progenitor of lithium-7 while leaving the other light elements alone. For a time, this was considered one of the most promising solutions to the lithium problem, a beautiful synergy between the puzzles of dark matter and primordial nucleosynthesis. But this path too has grown cold and fraught with peril. Supersymmetry makes a bold prediction. If it is real, we should be able to create these heavy superpartner particles in our most powerful particle accelerators. For years, the Large Hadron Collider at CERN, the most powerful machine ever built by humanity, has been smashing protons together with unimaginable energy, searching for even a fleeting glimpse of a selectron or a neutralino. And it has found absolutely nothing. The silence from the LHC has been deafening. With every new experiment that fails to find evidence for supersymmetry, the theory is pushed into ever more contrived and unlikely corners. The beautiful, simple versions of SUSY are now all but ruled out. The cosmic saboteur, the neutralino catalyst, is beginning to look less like a prime suspect, and more like another phantom that exists only in our theories. This leads us to the final, and by far the most audacious proposal on the path of new physics. It is a proposition so profound it borders on the philosophical. What if the problem isn't a missing particle, but a missing understanding of the laws themselves? What if the fundamental constants of nature, the numbers that underpin reality, the speed of light, the strength of gravity, the charge of an electron are not truly constant? What if they can change in time and space? This is a truly radical paradigm-shifting idea. We assume the laws of physics are immutable, the same here and now as they were everywhere, 13.8 billion years ago. But what if they're not a tiny variation in a fundamental constant, like the fine structure constant which governs the strength of electromagnetism, or the constants governing the strong nuclear force, could have dramatic consequences for Big Bang nucleosynthesis? The delicate dance of nuclear reactions in the first 3 minutes is exquisitely sensitive to these values. A slight increase in the strength of the nuclear force could alter the binding energies of nuclei, potentially suppressing the reactions that produce beryllium-7. A slight change in the neutron's lifetime could shift the initial ratio of protons and neutrons. It's conceivable that a very specific variation could be found that solves the lithium problem while preserving the correct abundances of hydrogen and helium. You would be rewriting the very code of the cosmos to fit the data. The implications are staggering. If the constants can vary, then our universe is a far more mutable and perhaps less predictable place than we ever imagined. But as with all of these new physics solutions, it faces an immense evidentiary hurdle. How can you prove the laws of physics were different at the dawn of time? Scientists search for clues by looking at the light from the most distant quasars. As this light travels across billions of light years to reach our telescopes, it passes through ancient gas clouds. The atoms in these clouds absorb the light at very specific frequencies which themselves depend on the fundamental constants. By analysing these absorption lines, we can in principle test whether the fine structure constant was the same billions of years ago as it is today. The results so far are tantalising, controversial and deeply inconclusive. Some studies hint at a tiny variation, others find nothing at all. The measurements are pushing the very limits of our technology, haunted by systematic errors that are fiendishly difficult to eliminate. We are left once again without a smoking gun. We stand at a crossroads, having explored the two great paths laid out before us. One path led us deep into the hearts of stars, a familiar landscape governed by known physics, but the clues there were ambiguous, the primary suspect seemingly exonerated by the curious flatness of the Spite Plateau. The other path took us into the theoretical fog of new physics, a realm of phantom particles, supersymmetric catalysts and shifting constants. Here we found elegant solutions in abundance, but each one was a ghost, a story told without a shred of independent verifiable evidence. The two search parties have returned and neither has found the missing treasure. The chasm between theory and observation remains as wide as ever. The lithium problem has resisted our best efforts, stubbornly refusing to be explained by either a flaw in our astrophysics or a simple, elegant tweak to our cosmology. It has become a quiet crisis, a persistent, nagging anomaly that challenges the very core of our understanding. To solve it, we may need more than just better theories. We may need a new way of seeing. So where do we turn now when the most obvious paths have led to dead ends? To find the missing lithium, perhaps we need to look not just farther out into the cosmos, but to entirely new messengers, to novel ways of interrogating the ancient universe for the secrets it still keeps. And so, we find ourselves at a profound impasse. A chasm has opened between the story the universe tells us and the one our theories predict. On one side, the crystalline logic of Big Bang Nucleosynthesis, a pillar of modern cosmology so successful, so elegant, it feels like a transcription of creation itself. On the other, the silent testimony of the ancient stars, the firstborn suns, whose atmospheres are stubbornly, inexplicably deficient in the universe's third element. The cosmic microwave background has given us the precise recipe, the baryon to photon ratio, the one number to rule them all. With it, we perfectly bake the primordial pies of hydrogen and helium. Yet when we get to lithium, the cosmos seems to have thrown away more than half the ingredients. This isn't a minor accounting error. It is a deep, fundamental contradiction, a flaw in the story that suggests either the universe is hiding a secret, or our understanding of its birth is dangerously incomplete. The stalemate cannot hold. Humanity's restless curiosity, our innate refusal to accept a paradox, is now marshalling a grand assault on this mystery from three fronts. This is the story of that assault. A relentless modern-day quest waged in the deepest mines on Earth, at the focal points of colossal telescopes, and on the bleeding edge of theoretical physics where the known laws of reality begin to fray. Our first front line is in the sky, a campaign of cosmic archaeology. For decades we have relied on the Spite Plateau, that curious flatlining of a lithium abundance in the oldest stars of our own Milky Way. But what if our galaxy is not the most pristine environment? What if, even in their infancy, these local stars were somehow subtly altered their primordial message, slightly corrupted by the complex chemistry of the nascent Milky Way? To solve this, we must look further afield. We must find stars that are not just old, but archetypically ancient. Cosmological hermits living in quiet isolation far from the turbulent metropolis of our own galaxy. The search takes us to the galactic halo's ghostly suburbs, to the faint ethereal dwarf galaxies that orbit our own like forgotten memories. These are celestial fossils, relics from a much earlier, simpler time, less processed by the relentless churn of stellar life and death. Within them, astronomers are now hunting for the faintest of the faint ultra, metal-poor stars' suns, with atmospheres so clean, so devoid of later elements, they are almost pure hydrogen and helium, direct windows back to the universe's first billion years. This is a new kind of stargazing, an act of supreme patience and power. It requires instruments of almost unimaginable sensitivity, telescopes, like the European Southern Observatory's Very Large Telescope, or the twin giants of the Keck Observatory in Hawaii. These are our time machines, their vast mirrors drinking in photons that have been travelling through the void since before the Earth was formed. Each photon is a clue. Each spectrum painstakingly captured over hours of staring at a single, unassuming point of light is a line of text from the universe's opening chapter. And the James Webb Space Telescope, with its infrared eyes, is peering even deeper into the cosmic dawn, capable of dissecting the light from stars and galaxies previously hidden behind veils of gas and dust. The goal is to expand our library of primordial witnesses to see if the Spite Plateau holds true in these isolated ancient realms. If stars in the sextans dwarf spheroidal galaxy or the Sculptor galaxy, show the same lithium deficit, the problem deepens, anchoring it more firmly in the physics of the Big Bang itself. But if by some miracle we find a population of stars with the full predicted amount of lithium, it would be a revolution. It would mean the solution isn't in the Big Bang at all, but in some unknown complex stellar process that over eons efficiently and mysteriously destroys lithium inside the oldest stars. Every new observation holds the potential for a breakthrough, but so far the silence from the stars is deafening. Every new ancient star we find seems to tell the same broken story. The deficit appears to be universal, a feature not of stellar evolution, but of the universe's fundamental nature. The evidence from the heavens is hardening, forcing us to turn our gaze from the infinitely large to the infinitesimally small, to the second great front in this war, the nuclear furnace itself. Our predictions for Big Bang Nucleosynthesis are not abstract mathematics. They're a direct result of tangible, measurable physics. The entire calculation hinges on something called a nuclear cross-section, a term that sounds complex but is beautifully simple in concept. Imagine it as the stickiness of two atomic nuclei. It's a measure of the probability that two particles colliding at a specific energy will actually fuse together and undergo a nuclear reaction. If you get these cross-sections wrong, even by a tiny amount, your entire prediction will be skewed. The BBN code is a vast network of dozens of these reactions, all happening in the chaotic soup of the first few minutes. For decades, we believed we had these numbers nailed down. But what if there was a subtle error in one of the key pathways, a reaction rate we thought we knew, but didn't? To find out, we cannot simply trust old textbooks. We have to recreate the Big Bang's crucible right here on Earth. This quest takes us to one of the quietest places on the planet, a place deliberately shielded from the universe, deep beneath a mountain. Welcome to the Laboratory Nazionale del Gran Sasso in Italy, and its flagship experiment Luna, the Laboratory for Underground Nuclear Astrophysics. Here, buried under 1,400 meters of solid rock, scientists are shielded from the constant rain of cosmic rays, the background radiation that bombards the Earth's surface. This cosmic silence is absolutely essential, because the reactions they are trying to measure are extraordinarily rare. At the surface, the signal would be utterly drowned out by noise. Down here in the heart of the mountain, they can listen for the faintest whispers of primordial physics. Inside Luna's accelerator hall, a scene of profound dedication unfolds. A particle accelerator, small by CERN standards but exquisitely precise, generates a beam of protons or deuterons. This beam is then fired at a target, a small piece of material containing, for instance, beryllium or deuterium. The scientists are trying to force the exact same nuclear collisions that governed the fate of lithium 13.8 billion years ago. They are meticulously remeasuring the stickiness of the particles that create and destroy lithium. One key reaction under intense scrutiny is the fusion of deuterium with beryllium-7, a process that produces boron-8. Another is the capture of a neutron by beryllium-7, which creates lithium-7. The work is painstaking, almost agonizingly slow. They tune the accelerator to the precise energies of the early universe, a temperature of billions of degrees Kelvin, and then they simply count. Using hypersensitive detectors, they count the individual gamma rays or charged particles that are the telltale signature of a successful fusion event. It is the ultimate act of cosmic forensics. For years, the international team at Luna and other similar facilities around the world has been refining these numbers, pushing the boundaries of precision. They have remeasured, cross-checked and debated every single value that feeds into the BBN calculation, and the result a triumph of experimental physics and a deepening of the mystery. The nuclear data has been largely confirmed, and in some cases made even more precise. These refinements have slightly shifted the predicted values, but they have not come anywhere close to bridging the gap. If anything, the more accurately we measure the physics, the more confident we become that our standard model of nucleosynthesis should produce 3 times more lithium than we see. The laboratory, like the observatory, is pointing away from itself. The problem does not seem to be in the stars nor in the known interactions of matter, which leaves only one place left to look. The most exhilarating and terrifying place of all, the fundamental laws of physics themselves. This is the third and final front waged not with mirrors or accelerators, but with the pure power of human imagination and mathematical reason. This is the realm of the theorists. If our observations of the cosmos are correct and our experiments on its building blocks are correct, then the flaw must lie in the story we're telling. The standard model of cosmology, for all its spectacular success, might be missing a crucial character. An unknown actor who took the stage in the first few minutes, altered the script, and then vanished without a trace. The search for this ghost in the machine of creation has become one of the most fertile grounds for new physics. It's a place where scientists are allowed to ask the most profound what-if questions. What if, for instance, dark matter is more complicated than we think? The standard picture treats it as a cold, aloof substance that interacts only through gravity. But what if some form of dark matter was unstable? Imagine a heavy exotic particle forged in the Big Bang's fire that lived for only a few minutes or hours before decaying. This is the decaying dark matter hypothesis. The decay of such a particle would release a flood of high-energy particles, photons, electrons, or even neutrons into the primordial plasma. This late-time energy injection would have occurred after. The primary creation of helium and deuterium was already complete, leaving their successful predictions largely untouched. But delicate fragile nuclei like lithium-7 and beryllium-7, which were still floating in the cosmic soup, would be exceptionally vulnerable. A high-energy photon or neutron could slam into one of these nuclei and blast it apart, a process called photodisintegration. In this scenario, the universe did create the right amount of lithium. It just moments later subjected it to a celestial blowtorch, destroying the evidence. This idea is profoundly compelling because it links two of cosmology's greatest mysteries, dark matter and the lithium problem, into a single unified story. The challenge is to build a model where the decaying particle has just the right lifetime, just the right energy, and just the right decay products to destroy enough lithium-7 without messing up the abundances of anything else like deuterium or lithium-6. It is a cosmic tightrope walk of incredible difficulty. But this is not the only radical idea on the table. Other theorists are tugging at an even more fundamental thread of reality, the constants of nature. We assume that the laws of physics are immutable, that they are the same everywhere, and have been for all time. But what if they're not? What if a fundamental constant, like the fine structure constant which governs the strength of electromagnetism, or the binding energy of deuterium, had a slightly different value during the era of Big Bang Nucleosynthesis? A tiny shift in one of these bedrock values of our universe would change the delicate balance of the four fundamental forces. It would alter the stickiness of nuclei, speeding up some reactions while slowing down others. Theorists have shown that a small, carefully chosen variation in these constants during that critical window could in principle suppress the production of lithium-7, while again preserving the successful predictions for the other light elements. This is a mind-bending proposition. It suggests the very framework of our reality might be pliable, evolving over cosmic time. It's an idea that many physicists find unsettling, a violation of the elegant simplicity they seek in nature's laws. Yet the lithium problem is so persistent, so stubborn, that even these extraordinary possibilities must be considered. They are testable in a way. By looking at the light from the most distant quasars which has travelled for billions of years, astronomers can check if the spectral lines of atoms have shifted over time, a potential signature of changing constants. The data so far is inconclusive, but the search is on. Beyond new particles and changing constants lies an even wilder frontier non-standard cosmology. We assume the early universe was almost perfectly smooth and uniform. But what if it wasn't? What if there were exotic phenomena, like in homogeneous pockets where the ratio of baryons to photons was different from the average? Or perhaps something stranger, like the influence of extraspatial dimensions predicted by string theory, which could have altered the expansion rate of the universe during that crucial epoch. Each of these ideas represents a departure from the standard narrative, a willingness to believe that the first 3 minutes were stranger, more complex and more chaotic than our simple, elegant model allows. Each theory is a bold attempt to write a new origin story, and each one must survive a gauntlet of brutal tests. It is not enough to simply solve the lithium problem. Any new theory must also be compatible with the near-perfect measurements of the cosmic microwave background. It must not upset the delicate balance of deuterium and helium. It must not contradict everything we know from particle accelerators and astronomical observations. This is the intellectual struggle at its most intense. It is a battle of ideas where the grandest, most beautiful theories are pitted against the cold, hard facts of observation. So here we stand at the climax of the search. The observers with their giant mechanical eyes are pushing deeper into the cosmic past, searching for an uncorrupted witness. The experimentalists in the shielded quiet of their subterranean labs are reforging the elements, ensuring the blueprint we use is flawless, and the theorists with nothing but genius and imagination are dreaming up new universes looking for a crack in the edifice of known physics through which a solution might shine. The answer is out there encoded in the light of the faintest stars hidden in the probabilities of a nuclear reaction, or lurking in the shadow of a new undiscovered law of nature. We are closer than ever before, yet the final truth remains tantalizingly out of reach, a final cryptic secret from the dawn of time. Finding it will require more than just bigger telescopes or more powerful accelerators. It will demand a breakthrough in our very conception of the cosmos. The answer, when it comes, will not simply close a chapter on a nagging problem. It will redefine the book itself, forcing us to rethink the story of us, the story of everything right from the very first page, undefined. And so, after this long and arduous journey, we arrive here, at a place of profound, unsettling silence. We have followed the evidence from the most ancient starlight. We have descended into the subatomic realm of the particle accelerator. We have modelled the first 3 minutes of creation itself with the most powerful supercomputers humanity has ever built. Every path we have taken, every brilliant theory we have tested, every potential solution we have chased to its logical conclusion has led us not to an answer, but back to this same imposing wall. Back to the stubborn, unyielding fact of the missing lithium. The cosmic accounting is still wrong, the books refuse to balance, and the universe offers no explanation. It is a uniquely frustrating position in modern science. We stand at the pinnacle of a theoretical edifice, Big Bang Nucleosynthesis, a triumph of human intellect that has successfully predicted the abundances of hydrogen, of helium, and of deuterium with breathtaking precision. It is a theory that has passed every other conceivable test, a cornerstone of the entire standard model of cosmology, our fundamental story of where everything came from. And yet, in the face of this one single discrepancy, this seemingly minor detail about one light element, the entire magnificent structure shudders. The dissonance of this single sour note threatens to spoil the entire cosmic symphony. It feels like a failure, a deep and humbling intellectual defeat. We have thrown the full force of our ingenuity at this puzzle, only to be met with an unblinking cosmic stare. The temptation is to feel lost to see this impasse as an end. But this right here is where the true power of science is revealed, because this frustrating, maddening, unsolved mystery is not a failure of the scientific method. It is its most glorious and vital expression. Science is not a collection of immutable facts, a sacred text of cosmic laws handed down from on high. It is a living, breathing, evolving process of interrogation. It is the art of being humble in the face of the unknown. A true scientific theory is not defined by what it can explain, but by its willingness to be broken. Its strength lies not in its infallibility, but in its falsifiability. A theory that cannot be challenged, that has no potential for error, is not science at all. It is dogma. The standard model of cosmology is not powerful because it is perfect. It is powerful because it makes predictions so precise, so daringly specific, that a single contrary observation, one persistent anomaly, can hold its feet to the fire. The lithium problem is that fire. It is the ultimate stress test, the one stubborn loose thread that we cannot help but pull, wondering if the entire tapestry, so beautifully and carefully woven, might begin to unravel. This is not the first time we have stood at such a crossroads. History is filled with these beautiful paradigm-shattering anomalies. For decades, the orbit of Mercury vexed astronomers. It refused to conform to the elegant predictions of Newtonian gravity, its path wobbling by a minuscule yet undeniable 43 arcseconds per century, more than the laws of Newton would allow. It was a tiny error, a rounding error for most practical purposes, and it could have been ignored, dismissed as a measurement flaw. But it wasn't. That tiny crack in the foundation of classical physics was the exact foothold Albert Einstein needed to build a new reality, a universe where space and time were not fixed, but a dynamic fabric that could be warped and curved by mass and energy. From that one stubborn anomaly, general relativity was born. Later, another puzzle emerged from the study of light and heat. Classical physics predicted that a perfect theoretical object, a black body, should radiate an infinite amount of energy at high frequencies, an absurdity that was called the ultraviolet catastrophe. The models worked perfectly at low energies, yet failed spectacularly at the high end of the spectrum. It was another nagging discrepancy, another loose thread. And from the effort to resolve it, Max Planck and his contemporaries were forced to invent an entirely new, bizarre and revolutionary way of understanding reality. They gave us the quantum, the idea that energy was not a smooth continuum, but came in discrete, indivisible packets. The world of quantum mechanics, the foundation of our entire digital age, sprang from the courage to take a single anomaly seriously. The lithium problem now stands as a sentinel in that grand tradition. It is the modern equivalent of Mercury's strange wobble, the 21st century's ultraviolet catastrophe. It is a message whispered from the dawn of time, telling us that our story of the universe, for all its power and beauty, is not yet complete. This is the true significance of the cosmic lithium deficit. It is so much more than a simple chemical imbalance. It represents a potential crack in the very bedrock of our understanding. It forces us to ask the most profound and unsettling questions. What if the physics of the primordial furnace, that first frenzied moment of creation, was more complex than we ever imagined? The standard model of particle physics, our best theory of matter and forces, is itself known to be incomplete. It has no explanation for gravity, no candidate for dark matter, no reason for the dominance of matter over antimatter. Could the solution to the lithium problem be hiding in that uncharted territory? Could there have been an exotic, unstable particle forged in the Big Bang, one that is not in our textbooks, which lived for just a fraction of a second before decaying in a way that altered the cosmic chemistry? Perhaps its decay products destroyed the fragile lithium nuclei, or maybe they catalyzed reactions that produced more helium, subtly shifting the elemental balance in a way our current models miss. This isn't just idle speculation. Theories of supersymmetry, which propose that every known particle has a heavier unseen superpartner, offer potential candidates for just such a particle. The lithium problem has become a powerful, if indirect, testing ground for these advanced frontier ideas in theoretical physics. Or perhaps the error lies not in some new exotic particle, but in our understanding of the fundamental constants of nature themselves. We assume that the laws of physics, the strength of the electromagnetic force, the mass of the proton and the neutron have been the same for all 13.8 billion years of cosmic history. But what if they haven't? What if in the extreme high energy environment of the early universe, these constants had slightly different values? A tiny shift, a change of less than a fraction of a percent, could dramatically alter the delicate nuclear dance of BBN, potentially resolving the lithium discrepancy, while leaving the other elements largely untouched. This idea is breathtaking in its implications. It suggests a universe whose fundamental character is not static, but has evolved over time, a concept that would force us to rewrite not just cosmology, but all of physics. This is the power of the lithium problem. It is a cosmic anchor holding us tethered to reality, preventing our theories from drifting into pure mathematical fantasy. It is a constant, humbling reminder that observation and experiment are the ultimate arbiters of scientific truth. It does not allow us the comfort of a finished story. Instead, it fuels the next great age of discovery. This single, stubborn number is one of the key scientific drivers behind the next generation of astronomical observatories. Telescopes like the James Webb Space Telescope and the upcoming Roman Space Telescope are peering further back into cosmic dawn, searching for the universe's very first stars and galaxies with unprecedented clarity. By studying these pristine ancient systems, we can create even more precise maps of the universe's primordial composition, sharpening the contours of the lithium problem itself, either confirming the discrepancy beyond all doubt, or perhaps revealing some subtle astrophysical process in these early stars that could finally provide an answer. At the same time, on Earth, nuclear physicists are continuing to refine their experiments. They are recreating the conditions of the Big Bang in miniature, smashing atoms together with incredible precision to remeasure every single nuclear reaction rate that plays a role in BBN. They are hunting for tiny errors in our laboratory data, any unaccounted for resonance or reaction pathway that might resolve the issue without resorting to new physics. It is a painstaking, meticulous process, a testament to the rigour and integrity of the scientific community. No stone is being left unturned. And that is the ultimate takeaway from this grand cosmic mystery. The lithium problem is not a sign of weakness in our quest for knowledge. It is the very engine of that quest. It is a beacon illuminating the edge of our understanding and showing us precisely where to push next. It is a source of inspiration for a new generation of scientists, the theorists, who will dream up the next universe, altering ideas, and the experimentalists who will design the clever new ways to test them. This is how progress is made, not by finding easy answers, but by wrestling with the hard questions, by having the courage to confront the data that doesn't fit, and by embracing the discomfort of not knowing. The universe, it seems, is under no obligation to be simple. It does not owe us a neat and tidy narrative where every chapter concludes with a satisfying resolution. Its beauty lies not in its simplicity, but in its inexhaustible layered and often bewildering complexity. We began this journey seeking to understand the origin of the elements, the very stuff of which we are made. We learned how the first 3 minutes wrote the opening chapter of our cosmic story, forging the hydrogen and helium that would one day fuel the stars and form the galaxies. We thought we had the story right, but the universe left us a clue, a single elemental ghost haunting our most successful theory of creation. This missing lithium is more than just a chemical anomaly. It is a profound lesson in cosmic humility. It reminds us that for all our incredible progress, for all the breathtaking power of our science, we're still just beginning to read the book of the cosmos. We are children on the shore of a vast and magnificent ocean, and while we may have mapped our own little bay with remarkable detail, the true extent of the deep uncharted waters remains a mystery. The lithium problem is a whisper from that deep ocean, a promise of wonders and revelations yet to come. It is the universe's way of telling us that the greatest discoveries still lie ahead, hidden in the very places where our knowledge fails. It assures us that the adventure is not over. In the end, we may never solve it in our lifetimes. Like a great unfinished work of art, it may remain a testament to the limits of our reach, but the pursuit itself will have changed us. It will have forced us to build better instruments, to invent new mathematics, to imagine new realities, and it leaves us finally with the most precious gift that science can offer, a deeper, more profound, and more enduring sense of awe. The universe is not a solved puzzle. It is an invitation to question, to explore, and to wonder. And that perhaps is the most beautiful answer of all.